Hello everyone. This is Yangzhe Liu, a master student at the Johns Hopkins University. Today I'm going to present our paper at EMBC2021, Analysis of Human Head Motion and Robotic Compensation for PET Imaging Studies. Positron emission tomography is a prime imaging modality for neuroscience research because it provides functional imaging of brain activities. Conventional PET scanners are large pieces of equipment optimized for scanning the whole body and require subjects to lie still on a scanning bed, and thus subjects are unable to move during scanning. This restriction led to the development of wearable PET imaging system called helmet PET, a concept that has since been investigated by others. The pictures shown at below in left half are some examples of current wearable system. For example, PET head, helmet PET, and mind tracker. However, the problem with a wearable system is that the PET imaging device is too heavy, or if it is made light enough, it loses sensitivities. Thus, we consider a mobile PET imaging system with robotic motion compensation, where the subjects can walk on a treadmill. The system includes a parallel robot, mobile PET imaging ring, and helmet. Robot is connected and able to control the PET image ring. Image ring will accommodate the movement of a helmet. The helmet or the head motion can be measured by the camera on the image ring tracking markers on the helmet, or by the multiple string encoders connected between the image ring and helmet. This paper presents the first step towards this approach, which are to analyze human head motion, determine initial design parameters for the robotic system, and verify the concept in the simulation. We utilized two datasets in this paper, raw motion capture data and IMU data. Both were collected in a previous study by Dr. Carolyn Paquette's group. Motion capture data is full body motion or position data from 16 healthy control subjects. The subjects were recorded during the overground walking in a straight line, captured by a motion capture system with sampling frequency 60 Hz. There are 45 reflective markers placed on the subject to collect the position in a fixed wall frame, as shown in the picture. The inertia measurement unit IMU data is the acceleration data from 8 healthy participants walking on a treadmill with sampling frequencies 128 Hz for validation. Then we are going to pre-process the motion capture data to emulate the treadmill walking. We used a left eye head markers to indicate the head motion. Because we're only interested in head motion during the treadmill walking, we subtracted the motion due to the overground walking, which we estimated by the fitting a line to the data from one body marker and C7, the cervical vertebra. Also, there are outliers present in the beginning and the ending stage of each dataset, corresponding to the time before and after the subject performed the overground walking. We search for the outliers only at the first or the last 20% data. If outliers occurs, we eliminate the data segment. Then we calculated the velocity and acceleration from the processed motion capture data using the central difference method. To verify the emulated treadmill head motion from the motion capture data, we first compare acceleration calculated from the motion capture data with IMU data statistically through the histograms. And then we utilize fast Fourier transform to verify their spectral properties. After this, we assume the initial design parameter for the robotic system is helmet has dimension 263 mm times 215 mm with image ring diameter 300 mm. We have 18 mm clearance in AP direction and 42 mm in ML directions. And then we simulate the effect using the robot to compensate for the measured head. One simple model for a robot system is a low-pass filter, which attenuates high-frequency signals and also imposes a delay or the phase change. or the phase shift. Our analysis indicates that the head motion is primarily within the typical robot bandwidth, 1 to 20 Hz, so we can adopt an even simpler model of just a time delay. Specifically, we provide the processed head position data described above as the commanded position to the simulated robot and use the delayed commanded position as the actual robot position. We evaluate with different delays to provide guidance into the design and the requirement of the robot system. Subtracting the delayed output from the input indicates the displacement of the head from the center. To avoid collision with the image ring, this displacement should be smaller than the clearance between the helmet and image ring. After processing the motion capture data and eliminate the outliers, we calculated the velocity and acceleration using the central difference method. This figure shows a simple plot of motion result for one human subject. We then plotted histograms of the acceleration estimated from the motion capture data and from the IMU, as shown in the left figure. The upper half is the IMU data and the lower half is the processed motion capture data. We verified that a normal distribution would be a reasonable model. Also, motion capture data share the similar statistical properties as the IMU treadmill data. In addition, we applied fast Fourier transforms on the measured head motion and on the IMU acceleration data, as shown in the right plot. This plot demonstrates that the processed motion capture data and the IMU treadmill data share similar spectral properties, with most frequency below 5 Hz. We then simulated the effect of using a robot to compensate for measured hand motion, where the robot was modeled as a time delay. The motion capture sampling frequency was 60 Hz, so we considered the time delays that were multiple of the sampling period, from 16.7 milliseconds to 166.7 milliseconds. The uncompensated head motion was given by the difference between the measured head position and the robot position. This figure shows the result in the AP and ML direction for a delay of 66.7 milliseconds, about 4 samples delay. The horizontal dashed lines indicate the 18 mm clearance in AP and 42 mm in ML based on the preliminary design. We then apply 3 sigma rules on the uncompensated motion in all 3 directions under different delays. 3 sigma rules means 99.7% samples fall into the limit. From the table, we can find where the 3 sigma motion under 100 milliseconds delays fall within the clearance. To explore the design parameter under different delays, the figure shows the required clearance for AP and ML direction between the helmet and image ring as a function of the robot delay time, where the clearance is based on the maximum in solid line or 3 sigma in dashed line for uncompensated head motion. To conclude, in this study, we analyzed recorded human motion to enable the design of the robotic system that can support a heavy imaging ring around a human head, and move the ring to accommodate normal head motions during the treadmill walking. We conclude that the processed motion capture data sufficiently represent hand motion during the treadmill walking to support the design of the robot system. The result also indicate that the preliminary design of a 300 mm diameter image ring with clearance of 18 mm and 42 mm in AP and ML direction is sufficient for robot delay up to about 100 milliseconds. For larger delays, it would be necessary to increase the image ring diameter to avoid collision. Our future work includes evaluation with physical robot, where the dynamic performance would be more complex than a fixed time delay. Thank you.